Hi, welcome to this lesson on Trigonometry, Trig Identities Part 2. Let's have a look at question 4. We want to prove the following identity and state any restrictions in that interval, if there are any. Well, first of all, on the left-hand side, I have a cos 2a and a sin 2a term. Now, I can put any angle a there, and cos and sin will always give me a number, generally between -1 and 1, because that's the range of the standard cos and sin graph. But with 2 here and all that, the range could be different. The goal or the piece of information that we are more interested in is that you can put in any angle and you will still get a real number out. Similarly, for the right hand side, there's cos and sine angles only, so I would say there are no restrictions in here. Okay, restrictions you're generally looking for when there are terms like tan, or if they are like square roots or fractions where we can't have negative inputs in a square root, for example. We can't have division by 0, for example. Those are the sort of things you'll look for when you look for restrictions. Okay, so both sides look quite complex, so I might end up working with both terms. We don't know yet, but I like expanding things out and simplifying them. So I think I'll start my proof off with the right-hand side. So that's 3 cos a plus sine a, and then times cos a plus sine a. All right, and if we expand those terms out, all right, FOIL or distribute them out. So 3 cos a times cos a is 3 cos squared a. 3 cos a times sine a is 3 cos a sine a. Sine a times cos a is just sine a cos a. And then sine a times sine a is sine squared a. All right. But now I notice a few terms here. So 3 cos squared a and a sine squared a. So I'm just going to group those together for now. So 3 cos squared a plus sine squared a. And then these terms are the same. Okay, so there's 3 amounts of cos a sine a and 1 amount of cos a sine a. So there are 4 amounts of sine a cos a. Now that to me is pretty interesting. So on the left hand side I need a 2 sine 2a. Alright, but I know from my double angle formulae, if I rewrite it like this, so 3 cos squared a plus sine squared a plus 2 times 2 sine a cos a, okay, because that still gives you this. Now 2 sine a cos a, that is sine of 2a. So already now I have my 2 times sine of 2a term on the left hand side, plus this other expressions here, 3 cos squared a plus sine squared a. So all I need is a cos 2a and a plus 2. If I can get that coming out of this expression, then we're done. Okay, so let's think about how we can do this. So let's get another color out here. So I can rewrite this as 1 amount of cos squared a plus sine squared a plus 2 amounts of cos squared a. Okay, because that cos squared a plus 2 cos squared a still give me 3 cos squared a. But the reason why I wrote it like this is because cos squared a plus sine squared a, that's equal to 1. That's a famous trig identity. So this now becomes 2 sine 2a plus 1 plus 2 cos squared 2a. Okay, but we want cos 2a plus 2. So what I'm going to do at this point now is I'm going to work with the left-hand side and simplify it and see if it just ends up being this term here. So left-hand side, we have that 2 sine 2a, that's fine, plus we have 2 plus cos 2a. Now, cos 2a, right, there are 3 variations, but I want to pick one that's going to make sense in my proof here. So I see a 2 cos squared a, and I know that cos of 2x can be written as 2 cos squared x minus 1. That's one of the 3 variations. So I think I'll use this one here. So it's going to be plus that 2 plus cos 2a, I'm going to write as 2 cos squared a minus 1. So now simplifying that, I have 2 sine 2a plus 2 cos squared a minus 1. The 2 and the minus 1 will just leave you with plus 1. So you have 2 sine 2a plus 1 plus 2 cos squared a. And this is exactly the same expression as the one we've just derived for the right-hand side. So therefore, we've shown that the left-hand side is equal to the right-hand side, and we have successfully proven this trig identity. All right, so the important part here was to make sure that once we've simplified, we needed both expressions to look like each other. And then initially it wasn't looking like that. So when you get to a point where it almost looks like it could be the other side, then try the other side and see if you can simplify that further. And if you can, you'll eventually get to the expression that you already derived on the first side that you've picked. All right, so that's how we would solve this type of question. I'll see you in the next one.